Hey, welcome to the channel. So a while ago I came up with an idea for a really cool project after stumbling across a video of this dude who built a synthesizer from a Sega Genesis. From what I can immediately make out from his video, it seemed to me like he was using the Mega Drive to take in keyboard inputs from a MIDI keyboard of some sort and output them as an audio signal. He then built this panel that had a series of potentiometers that were presumably used to modify the outbound signal of the Sega Genesis. Like an analog signal processing kind of deal. Loved the idea, and I thought it seemed super impressive. The idea of building an instrument from a gaming console sounded really fun, and I had the idea to build something similar. First, I wasn't sure where to start until I caught a glimpse of what appeared to be a Gameboy instrument in the background of this gentleman's video. Coincidentally, and not long before watching that video, I had purchased a GBX cart from Inside Gadgets. Plus, I already had a ton of familiarity with the Zilog Z80 processor, which, give or take a few minor differences, is essentially the same processor used in the Game Boy. Figured some sort of Game Boy instrument would be the best route for what I was looking to build. Now some differences. This Sega Genesis instrument seemed to utilize analog signal processing to process the audio coming from the console. As opposed to analog signal processing, which is a huge paradigm in electrical engineering, I wanted to go about this from a more computer engineering approach. Just got dark in here all of a sudden. That is, with DSP, digital signal processing, or by manipulating the registers of the Z80 processor, turning the Game Boy itself into the instrument. As opposed to manipulating the audio coming from the Game Boy's audio output jack, you'd be able to attenuate the values in the sound registers in the Game Boy using potentiometers, or switches, or whatever. So then the question becomes, well, how do you go about building a Game Boy instrument? First, I think we need to actually take a look at how the Game Boy produces sound from a microprocessor standpoint. I've found a preponderance of resources online that reference the original Game Boy hardware, but not a ton related to the Game Boy Color. As such, a lot of what you'll be seeing in these videos will be from documents related to the original Game Boy, unless otherwise specified. Now, for a very general overview of the Game Boy architecture, I'm going to be referencing a lot of material I found online, most of which comes from a writing done by Rodrigo Capetti titled Game Boy Architecture, A Practical Analysis. There's a ton of information in these resources, and for the purpose of this video, I'll only be covering the details that are pertinent to this particular project, so I'll leave links to all the reference material in the description below for anyone interested in learning more. The original Game Boy uses a modified version of both the Zilog Z80 and Intel 8080 processors called the DMG CPU. This was updated in the Game Boy Color to the CGB CPU, which is mostly similar to the original, but with an increased clock speed from around 4 MHz to 8 MHz. Unlike previous consoles like the NES, which housed its APU, or audio processing unit, on a separate chip on its motherboard, the DMG and CGB CPUs were fabricated using a system-on-a-chip design approach, which allowed for other components, such as the APU and PPU, or picture processing unit, to be included on the same chip as the CPU. The APU within the Game Boy's CPU is a 4-channel PSG, or programmable sound generator, chips similar to those found in the NES and Sega Master System. This APU contains 2 pulse or square wave channels, 1 customizable waveform channel, and 1 noise channel. Each of these channels have 5 8-bit registers associated with parameters related to their respective channels, such as volume control, frequency, or sweep period. There are 3 additional registers responsible for the control and status of the sound chip that include left and right channel enable and volume controls, power control and status, and channel length statuses. In addition, the registers from addresses FF30 to FF3F contain the wavetable data for channel 3. That's 16 registers, each containing 2 samples for a total of 32 samples of waveform data. Channels 1 and 2, as we had just learned, are the square pulse channels and sound something like this. Although these channels consist of 1 square wave per channel, The tone of each wave can be adjusted by manipulating its pulse width or duty cycle. Other parameters include the starting volume, length enable, which enables the length counter, allowing it to be decremented, length load, or the time for each pulse, after which the channel stops, envelope add mode, which increases the amplitude of the volume envelope, period, or the period of the add mode envelope, frequency, or the note being played, and the trigger, which begins playback of the respective sound register. Unlike Channel 2, however, Channel 1 also includes frequency sweep parameters, which allow for the frequency of the square pulse to be moved up or down, which is typically used in games to produce sound effects. Channel 3 is the wave channel. Unlike the first two channels, this channel produces sound from 32 bytes of waveform data stored in memory. The period of this data can be attenuated to play various frequencies or notes, but has no means of volume control over a period of time. In other words, the volume must be set to 0%, 25%, 50%, or 100% prior to the triggering of the sound. The channel sounds something like this. Combined with the other channels, it sounds like this. Like the square channels, the wave channel has registers for length load, frequency, length enable, and trigger. Channel 4 is the noise channel and is responsible for generating noises like sound effects and percussion instruments. This channel utilizes a 15-bit linear feedback shift register, or LFSR, that acts as a random number generator to produce white noise. Here's what it sounds like with the other channels. Like the square channels, the noise channel has registers for envelope add mode, envelope period, length enable, length load, trigger, and volume. Other parameters for this channel include width mode of the LFSR, which when set reduces the size of the register from 15 bits to 7 bits, divisor code, and clock shift. So now that we have a better understanding of how the sound channels on the Game Boy work, we need to figure out how we're going to actually implement this. For one, we know we'll need a means of writing values to the sound registers. This can be done one of two ways: by sending the data to a program written to a cartridge by means of the Game Boy's serial link cable, or by writing to the CPU registers directly by means of the cartridge pins. While using the serial communication method would be the most easy to implement, being able to write to the CPU directly would have superior performance benefits over the serial communication protocol. This would also forego the need to write to the Game Boy cartridge altogether, since the game itself would be emulated by whatever we have hooked up to the cartridge pins. We'll also need a means of receiving values from various potentiometers, switches, and a MIDI keyboard. There are already a ton of resources online related to constructing similar MIDI controllers using various boards like microcontrollers and Arduino, and with that we need to consider the development platform that we plan on using. FPGAs, or Field Programmable Gate Arrays, are development boards for hardware prototyping. Programs written to FPGA chips are written in some form of hardware definition language, like Verilog or VHDL, and are capable of executing programmed hardware concurrently. Unlike normal programming languages and microprocessors that execute code sequentially, every instance of programmed logic on an FPGA executes at the same time. This would be especially useful for the communication method involving the cartridge pins, since the FPGA would simply act as a cartridge emulator. The downsides would be the cost, since FPGAs are generally more expensive than microcontrollers. An interaction with the outboard controls and MIDI keyboard, since interfacing with analog and USB inputs would be too troublesome to implement in VHDL. Microcontrollers like the Arduino Uno and STM32 are another viable option. There are several projects online already that involve interaction between microcontrollers and the Game Boy, so there's certainly no shortage of resources surrounding this approach. Building an interface with analog controls would be simple, but interfacing with the Game Boy would probably require a serial communication method unless the microcontroller we use has a fast enough processor, like an ARM Cortex. Previous research with Arduino boards that utilize the Atmega chips has shown that setting the cartridge pin values is infeasible within the time budget of the Game Boy system clock. Raspberry Pis, which are essentially just smaller computers, offer much greater performance benefits over microcontrollers, but come with fewer built-in features native to microcontrollers like the Arduino. While the CPU speed of even the older Pi models is greater than those of most common microcontrollers, they can be somewhat more pricey, although this platform would be ideal for interfacing with a MIDI keyboard. It seems to me at least that the Raspberry Pi would be the best platform for the development of this project, although I might end up using a combination of both the Pi and the Arduino to handle the control board. So I plan on turning the construction of this Gameboy synth into a multi-part series, so in future videos I'll cover every step from the prototyping, development, and construction process. If you like what you saw, I'll ask that you please consider subscribing. If not, let me know why in the comments below, and until next time.